Hello and welcome to the live lesson, if you will, for 5.06 Solubility and Concentrations. In this lesson we're going to talk through the different concepts in the lesson that you need to understand, and then at the end we'll look at some practice problems in regards to the math aspects of this lesson. First, I just want to highlight some of our objectives that we're going to go through as we're looking at this lesson. First off, we're going to identify different parts of solution and describe them in qualitative manners. Then we are going to identify and explain different factors that affect solubility and dissolving rate. So two separate things there. And then really the fifth item is we're then going to do some of the math problems where we actually determine the molarity and percent by mass for a solution. Now, prior to doing this lesson, we just want to mention that it is worthwhile to make sure you feel comfortable with lessons 1.06, 2.04, and 5.05. For 106, it's unit conversions. We will use unit conversions in this lesson. For 2.04, we're talking about the mole concept and converting grams to moles. Both of those things we will also be using in this lesson. And then from 5.05, the difference between mixtures and solutions. The main difference is that mixtures are heterogeneous, and we are going to be focusing on solutions throughout this lesson, which are homogeneous or homogeneous. Alright, so as just mentioned, homogeneous or homogeneous mixtures is a solution. What that simply means is they are evenly mixed throughout. A great example of that is, if we take like iced tea or lemonade, something like that. If you take, you have a pitcher of lemonade and you pour out a glass, the first glass you drink, tastes like lemonade. Then you get near the bottom of the pitcher and you pour out a glass and it still tastes like lemonade. It's the same stuff. And it's that way because it is evenly mixed throughout. Whereas something like, pretty much any, like Rocky Road ice cream is a great example we always use. That's a heterogeneous mixture because when you scoop out that ice cream, every spoonful is going to be a little bit different with what you actually get in there, whether it's caramel or fudge or whatever happens to be in there. Now in solutions there are two parts. We have the solute and the solvent. The basic difference: solute is the part being dissolved, the solvent is the part doing the dissolving, or what we call the dissolving medium. An example here, we have salt water. Okay, an easy way to remember the difference between the two, the one that is being added to the other one is going to be the solute. The one that's quote unquote receiving the solute, that would be your solvent. So in this case we are adding salt to water, so the solute would be the salt and the solvent will be the water. And in fact, in chemistry, majority of the time our solvent is water. So we call that the universal solvent. Okay, and that just indicates that we use it quite frequently. And really for our course, pretty much everything we talk about when we deal with solutions will be in water. Alright, so let's just look at three quick examples here and just determine what is the solute, what is the solvent. Again, the lemonade, I already kind of hinted at that one a little bit. We're taking the powdered sugar stuff and we are adding it to water. So again, the one that we add is the solute. So in this case that would be the lemonade powder. And what we are adding it to is the water. So that would be our solvent. All right, now the next one here is a unique solution in that we have gas in gas. Whenever we have a gas in gas type of solution, the rule of thumb is that the least amount of the each gas is going to be the solute. The one that we have a greater amount of is going to be our solvent. So when we look at those percentages, we would say that the oxygen and other gases is the solute, whereas the nitrogen would be the solvent. Okay, so this one's a little different from the first one. The first one, it was a solid and liquid. In this one, we have gas and gas. So we can have different types of solutions also. The last one, dilute sulfuric acid. We're taking sulfuric acid and diluting it. And of course, when we dilute things, we're adding water. We'll get into dilutions in 5.07. So here, the sulfuric acid would be our solute, and our solvent will be the water. Okay, so again, we have a situation where in this case we have an aqueous solution being added to a liquid. So we have different types of solutions we can make, but the key is just identifying what's being dissolved and what's doing the dissolving. Okay, so again, let's just talk about that dissolving process here for a moment. On the molecular level, there's a lot of things happening, but we can kind of categorize it into 3 steps, if you will. First, when you add, we'll use our salt water example. When you add the salt to the water, the solute particles are going to separate, and the reason for that is because the solvent particles begin to collide with them and causes their attraction for each other to be broken. The solvent particles will then kind of spread out and allow the solute particles to mix in or intermingle, if you will, with them. And then the final step is the solvent particles then themselves become attracted to those individual solute particles as they mix together. So using our salt water example, we take NaCl, which is table salt, and when we place that in water, it's going to break up into the 2 ions, Na plus and Cl minus. Now remember back in module 3, we learned that water is a polar compound, which means it has a positive in and a negative in. So if we take water and let's see here, and we draw a water molecule here. Oop. Okay, so we got our O. Remember, it's a bent shape, so we got the H over here. And then we got another H on this side. Okay, the oxygen, remember, has a higher electronegativity, so this end will be slightly negative. The hydrogens have a lower electronegativity, so that end will be slightly positive. So what happens then is the negative end of the water molecule is attracted to the positive ion and will surround it. And it'll be a bunch of water molecules doing that. And then the positive end of the water molecule, a bunch of those will surround the negative ion. And that is when the substance is said to be dissolved. Now, how well something dissolves, an important thing to note here at the bottom, is really dependent on the attractive forces. Basically, if the attractive forces between the solvent and solute are greater than the attractive forces between the particles within the solute, then you're going to have a situation where it will dissolve quite easily. If the opposite is true, if the attraction within the solute particle is stronger than the attraction between the solute and the solvent, then you're not going to have as much of a successful dissolving situation. So it's all about attractions, between those different particles as far as how well something does or does not dissolve. All right, now I mentioned that we are going to just briefly talk about the qualitative ways of describing solutions. A couple ways we do that is we just talk about saturation. Is it saturated or is it not? For something to be saturated, that means it contains the maximum amount of solute under those given conditions. In other words, at that temperature and pressure, it holds as much solute as it possibly can. Again, using our salt water example, if you have a glass of water and you add so much salt to it that no matter how much you stir it, there's still salt sitting in the bottom of the glass, you have made a saturated solution because we're not able to get any more salt to go into the solution. An unsaturated solution would be anything less than that. So for an unsaturated solution, again, if we had the glass of water, we add a little bit of salt, stirred, it dissolves. We add a little bit more salt, dissolve, stirred, and that dissolves. So we have an unsaturated solution in that case because it is less than the maximum amount. Now, important here to understand that unsaturated, it could be, very little amount of salt. It could be a lot of salt. As long as it's less than the maximum it can hold at that temperature and pressure, it is considered unsaturated. So it is very much a qualitative term because it's obviously dependent on whether or not it's saturated. All right, so now the factors. First, the factors that affect solubility. In other words, how well something does or does not dissolve. First one is temperature. Now, temperature actually has different effects depending on if it's a solid or a liquid, or excuse me, a gas. If we're dissolving a solid in a liquid, the solubility will increase with increase in temperature. Reason being, if you go back to Module 6 and use collision theory and the kinetic molecular theory, it makes sense how this will work here. You increase temperature, which means you're increasing kinetic energy. With an increase in kinetic energy, the molecules are moving more quickly. Since they're moving more quickly, they're going to collide with each other more frequently. And as a result of those collisions, we're of course going to be able to break up the solute particles quicker. We're going to be able to have solvent and solute particles attract to each other quicker. So everything's just moving faster. So an increase in temperature will increase the solubility of a solid. For a gas in a liquid, it actually has just the opposite effect. The solubility decreases. Okay? Again, going back to the molecular theory here, you increase the temperature, the molecules are moving faster. Well, remember, for gases to be in liquids, we have to kind of, force them in there because a lot of times those gas particles actually want to escape and be free and float around, in the container, the room, wherever you happen to have the cup or bottle or whatever it is that we're talking about. So by increasing the temperature and the molecules are moving faster, those gas particles are able to escape more easily, so you're actually going to end up with less gas in solution. The way to think about this, if you're trying to get away from somebody, you obviously can get away from them faster if you're running than if you're walking. The same thing is true here for the gas particles. For them to get out of solution, they can do it more quickly when the particles are moving faster than if they're moving slower. Now the second factor, pressure, only works when we're dealing with gases. And this is something you experience with, soda cans or soda bottles. Solubility increases with an increase of pressure. Okay? The way to kind of think about it is, like I was mentioning a moment ago, the gas particles are forced into solution. So if you increase the pressure, you are going to force more gas particles into solution. And that's what they actually do when they manufacture soda and other carbonated beverages. is they are forcing gas into solution by using pressure. So when we open it and we hear that little, popping sound or hissing sound, it's because we are releasing that pressure, which is allowing those gas particles to come out of solution. So an increase in pressure increases solubility. All right, now dissolving rate. Dissolving rate is simply how fast the solute dissolves. And there's three things we can do to increase the rate of dissolving. First, we can increase the surface area. Basically, if you take a cube of sugar and put it in some water, it will dissolve, but it's going to take some time. If you take that same cube, crush it up into a powder, and put it into the water, it dissolves more quickly. Reason being, the powder has a greater surface area. In other words, there's more locations, if you will, or sites for the solute particle and the solvent particles to collide with each other. Since there's more opportunities for collisions, we're naturally going to have more collisions, which means it's going to dissolve faster. The second one, agitation, stirring, shaking, okay, those all can be considered agitation. If you stir the solution that you're trying to make, you are dispersing the solute particles throughout the solvent. Again, you are giving more opportunity for collisions between the solute and the solvents. More collisions, we're going to have the process move more quickly, so it's going to go faster. And then finally, the temperature. Again, you increase temperature, you're increasing the kinetic energy. So the particles are moving faster. Again, with particles moving faster, we're going to have more collisions, so everything's going to dissolve faster. So you can see all of it really goes back to that collision theory. A great example of all three of these at work is when we make hot chocolate or hot cocoa. All right, we're using a powder, so it has high surface area. We're stirring it, and we're using hot water. Okay, so we're using all three of those to help us get the powder dissolved in the water. Try doing it with cold water, it takes longer. Try not stirring it takes longer. If you have a chunk of the hot cocoa that or the cocoa powder, when you put it in there, again, it takes a while for that chunk to dissolve versus if it stayed in its powder form. All right, so those are three different factors that can help increase how fast something dissolves. All right, so now those are all the terms that we can use. Now let's look at the math aspect of this lesson. When we do concentration, there's many different ways we can represent the concentration. The two that we use most frequently in chemistry are molarity and percent by mass. And we're going to show you some sample problems for each of those. Molarity is simply moles of solute divided by liters of solution. So the key is making sure we just get everything in the correct units. If we look at the sample problem, what is the molarity of a solution in which 32 grams of KCl is dissolved in 525 milliliters of solution? All right, so we have grams of KCl, which is our solute, and we need it in moles. We have 525 milliliters of solution, we need it in liters. So the hard part is really just getting everything in the correct units, which goes back to our 106 lesson on unit conversions. So the first thing is to, of course, get them in the correct units. So we start with the 32 grams of KCl. To get it to moles, we need the molar mass. And just a reminder, we get molar mass from the periodic table. So this step right here is the molar mass, and remember we get that from the periodic table. So if we went to our periodic table, we looked up the mass of potassium, we would get 39.098, and the units are always grams per mole. And then we do the same thing for the Cl, and that mass is 35.4 5.453, and again it's grams per mole. Now in this example we have 1 K and 1 Cl, so we can just leave it as is, and then we just simply add those two numbers together to get the molar mass. So that's where the 74.551 comes from. It's simply adding 39 and the 35.45 together. Now I set it up with moles on top and grams on bottom, again so that we're canceling out units. Remember, when we're converting units, that's all we're doing, is trying to set it up so we cancel. So by putting the conversion with the 1 mole on top, 74.551 grams on bottom, we got grams on top, grams on bottom, so they cancel out, leaving us with the moles we're looking for. So our math here is 32 times 1 divided by 74.551. For the second step, we're doing the same type of thing. We have 525 milliliters, and we need it in liters. So our conversion, 1 liter equals 1,000 milliliters. And again, we put the liters on top, milliliters on bottom, so that the milliliters cancel out. And we end up with 0.525 liters of solution. Now we have everything in the correct units. We just plug into our formula. 0.429 divided by 0.525, and we end up with 0.818 molar, is how we say that, KCl. All right, so let's walk through another example together. This time we have 10 grams of AgNO3, and it's dissolved in 500 milliliters of solution. So again, we need to convert those units. So we take our 10 grams of AgNO3, and our 500 milliliters of solution. Alright, and we're going to convert these. Just going to go ahead and set up all the boxes here at once. Okay, now I'm going to go over here to the right so we can figure out that molar mass that we need. Alright, we go to our periodic table. Silver has a mass of 107.87. There is only 1 in the formula, so we just multiply by 1 and it stays 107.87. Nitrogen, same thing, go to our periodic table, and we have 14.007. There is only 1 of those, so we end up with 14.007. For oxygen, we have 15.99. There are 3 in the formula, right? When we look up here, AgNO3. So we have to multiply that one by 3. And that gives us 47.97. Okay, so we then would add those 3 numbers together to get our grand total for the molar mass. And we have 169.847. Again, the units are grams per mole. So that's what we will use in our conversion. Again, the 1 mole will be on top. And then on the bottom will be the 169.847. Alright, so 10 times 1 divided by 169.847. Moles Ag NO3. Alright, so now on the bottom, again, remember from our metrics that 1 liter is 1,000 milliliters. So that will give us 0.5 liters of solution. And then, of course, the final step is to simply take those two numbers and divide them. So we got 0.0589 moles AgNO3, and then on the bottom we got liters of solution. And that would give us a final answer of 0.118 molar AgNO3. Remember, make sure you include the compound formula there so we know what compound we're working with. Okay, and so that's how we do molarity. Now, percent by mass, this one's actually a little bit simpler. For percent by mass, we have the mass of the solute over mass of solution, and then to make it a percentage, we just multiply it by 100. So here we've got what is the percentage or percent by mass of a solution in which 15 grams of Na2SO4 is dissolved in 850 milliliters of water. Now this first step goes back to something that we learned back in like module 1, if I remember correctly, and that is that the density of water is 1 gram per milliliter. So for every 1 milliliter of water, we have 1 gram of water. So that helps us to make this nice easy conversion here. 850 milliliters, 1 gram over 1 milliliter, so the milliliters cancel out. So we have 850 grams of water. So now we just plug into our formula. Mass of the solute was 15 grams. Mass of the solution. Now remember a few slides ago we talked about that the solution is solute and solvent. So we have to add those two together to get the total mass of the solution. So we take the 15 plus the 850, and then when we do our math, we end up with 1.73% Na2SO4 by mass. And we do want to make sure we add on the by mass part, because as I mentioned earlier, there are other ways we can do this. We could do like by volume. So we also want to label it so others know how we solve this problem. So let's look at an example together here, walk through one. All right, what is the percent by mass of a solution in which 20 grams of HECl is dissolved in 50 milliliters of water? Well, again, if we have 50 milliliters of water, or excuse me, 500 milliliters of water, we have 500 grams of water. All right, now remember when we say water, that is our solvent, okay? All right, our universal solvent. So now we're just going to plug into our formula. Okay, so on top we've got 20 grams of AgCl. Then on the bottom we got 20 grams AgCl plus 500 grams of the water. And then again, we have to multiply it by 100 to make it a percentage. And that will give us 3.85% AgCl by mass. Okay, so pretty straightforward process with the percent by mass calculations. Just make sure that when you're doing mass of solution, you're including both the solute and the solvent. All right, so now that we've looked at the lesson, well, what do we need to do next? Well, first, be sure that you have gone through all parts of the lesson, the introduction, the lessons. Make sure you've clicked on all the hyperlinks that take you to different practice problems and samples that you can look at. If you're still needing some assistance, you can attend the open tutoring sessions to get some questions answered. You also can use the review sheets that we have in the Student Resource Center. And again, the links to both the open tutoring and the Student Resource Center are located on your announcement page, so you can easily access those to get that information. And once you've completed all of those activities, feel comfortable with the material, then you can go into the Assessments tab and complete the 5.06 quiz. You can also access that quiz through the gradebook. Either tab will get you there, but 5.06 and then take the quiz. And that'll have you finished with that one, and then you can move on to 5.07. Thanks for joining us, and we will see you again soon.